Now, once we've looked at the p-value and we've decided that we feel confident that the results have statistical significance, we can turn our attention to effect size. Effect size tells you how far apart the treatment and the placebo groups are. In psychiatry, many effective treatments have modest but real effects. In psychiatry, the most common ways to report an effect size are the Cohen's d, the d stands for difference, an odds ratio or OR, number needed to treat or NNT, and number needed to harm or NNH. Now, there isn't a magic number that says this is an effective treatment. Some studies will report the percentage of patients that had a response to a treatment, which typically means a 50% reduction in symptoms on a given measurement like the MADRS, and how many people went into remission. Remission is usually measured as a cutoff where the numbers are fairly low. To understand this, it's important to remember that not everyone in a study, regardless of whether they're in the placebo group or the drug group, are going to come out the same. So let's say what you're looking at here is the placebo group. Now, when we look at the results of the people that were in the placebo group, some of the people will not have done very well at all, and some are going to be doing better. This is just sort of a normal distribution of results, but most will have done kind of averagely well. There might be a little bit of improvement. Remember, we see some improvement even in the placebo group usually. But now we bring in our treatment group. Now, they've done better than our placebo group overall. You see this curve is more to the right. But these results are also normally distributed. Some are doing so-so. Some are doing really well, all the way over on the right. But most are doing considerably better. So this is the difference between the placebo group and the drug group. An odds ratio, which is abbreviated OR, tells you how much more the likelihood of an outcome is in one group over another. An odds ratio of 1 means that the outcome is equally likely in both groups. It means there's no difference between the two groups. Now, let's say that we have a treatment for a drug for depression. At the end of the study, 50% of the people on the drug met criteria for remission, and 25% met criteria for remission on placebo. So 50% divided by 25% equals 2. So we'd say the odds ratio is 2. Or another way you could say is that you've doubled your chances of remitting on the drug compared to placebo. A smaller odds ratio, smaller than 1, would mean that you're more likely to get better on the placebo than you are on the drug. Now, what if there was a way to break this down into an even easier to understand metric? The number needed to treat asks this question: how many patients need to get this treatment for one additional person to benefit? Now, bear in mind, most psychiatric treatments have an NNT between about 7 and 10. Now, understand that it doesn't mean that this is like playing the lottery, and if your NNT is 7, that one person gets all the benefit and the other 6 don't get any benefit. The way to think about this is that that benefit is distributed over that group of people. So the smaller number of people means the more potent the treatment is, the more effective the treatment is. Now, you can also flip this and look at side effects through this same lens using something called number needed to harm. And in that case, you're asking the question, how many people would I need to treat until I saw this side effect or this harm? And the bottom line here is that with NNT, number needed to treat, a small number is a great thing. And with NNH, or number needed to harm, we like to see large numbers. Now, what if we took all the studies that have been done on a particular treatment and compared them to each other to see what the consensus is? That's what's known as a meta-analysis, and it's a really useful tool in evidence-based practice. Now, there's a couple of pitfalls to look out for. Now, like baking a cake, your results are going to depend on the quality of the ingredients you put in the batter. So it's important to understand how they decided which studies to include and which to leave out. You usually see a diagram like this, a flow sheet that shows how they chose the articles and which ones were included and which ones are excluded. Now, it's also important to remember that scientific journals tend to like to publish positive results. They generally don't like to say, hey, we did an experiment and nothing happened. They're more excited to publish papers that show that a treatment worked. So there tends to be a little bit of a publication bias in meta-analyses because they're pulling from the studies that are in the literature, and those tend to skew towards the positive. Now, often these On the left, you can see citations of all the papers that went into the meta-analyses. And on the right, with that vertical bar, you can see the final analysis. Now, any study that falls to the left of the line is going to favor the drug treatment. And any study that falls to the right of the line is going to favor the placebo. At the very bottom of that right-hand column, you can see those little black diamonds. And those black diamonds show you the sort of sum total of the results and how large that sample size is. So anything to the left in this particular study favors the drug. So in this particular meta-analysis, we could say that there is reasonable confidence that the drug has been effective over multiple studies. Now, when you begin to understand effect sizes, you stop asking yourself, is this statistically significant? And you start asking yourself, is this worth doing for my patients? And that shift from numbers to judgment is what defines clinical expertise.